Hi friends, this is the 14th lecture in the lecture series for the preparation of GATE in mechanical engineering, and today we will be dealing with forced forced convection, and also we will be dealing with some significant dimensionless numbers. Okay, dimensionless numbers. So this is our today's lecture, and this is the continuation of last lecture. So please go through the previous lecture to get a better understanding. Okay, so let's start. First of all, let's write the dimensionless numbers. So we all know about this Nusselt number and this Prandtl number and also the Reynolds number. The first of all, the Reynolds number, which is nothing but the ratio of inertia force by viscous force, and which will give the relative magnitude of this inertia force and the viscous force. And then let's deal with the Nusselt number, and this Nusselt number is given by the equation HL by K, and this is also the ratio of conductive resistance to the convective resistance. In the last class, or the while we are dealing with the lumped capacity model, we have dealt with some dimensionless number called the Biot number, and this Biot number is also having the equation HL by K, and this is also the ratio of conductive resistance to convective resistance. And the difference is that in the Nusselt number, let's suppose we are having some fluid between two surfaces like this, and some fluid is in between these two surfaces. This is surface 2, and let's suppose if R conduction and R convection is about the fluid itself, or with respect to the fluid only, then we will be dealing with Nusselt number, that is HL by K. And if the R conduction is about the solid surface and R convection is about the fluid that surrounds the fluid, then in that case we will use HL by K as the Biot number, that is R, that is, I will summarize is that. And for this Nusselt number, HL by K, or the R conduction for the solid, for the fluid, and this R conversion for the same fluid. But for Biot number, the R conduction for the solid and this R conversion is the fluid that surrounds the solid. Okay, so that is the difference between this Nusselt number and the Biot number. So next dimensionless number is the Prandtl number, which can be determined by using the dimensional analysis. Okay, so in the experimental results, or from the experiments, we have determined that the thermal boundary layer thickness, that is given by the letter delta T, is a function of fluid properties like rho, mu, Cp, K, and the characteristic velocity V, and the hydrodynamic boundary layer thickness, which is given by the letter delta. So these are the fluid properties, and this is characteristic velocity of the fluid, and this is the hydrodynamic boundary layer thickness. Okay, and this delta T is the thermal boundary layer thickness. Okay, so we can reveal this function by using the dimensional analysis. And in this case also we are having number of variables equal to 7, which is the m, and the number of fundamental dimensions is 4, which is nothing but n. And from this 2 we can determine the pi terms, that is number of pi terms is equal to m minus n, which is nothing but 3. Okay, so we are having 3 pi terms, and we are determining this phenomenon of delta t by using the Buckingham pi theorem. And this is for Buckingham pi theorem. Okay, and by using the Buckingham pi theorem we can choose the repeating variables as density rho, and then viscosity mu, and the thermal conductivity k, and the characteristic velocity v as the repeating variables. Okay, and by using these repeating variables we can write the pi terms as the first pi term, that is pi 1, which is rho raised to a, mu raised to b, k raised to c, v raised to d into delta t, and which reveals the first pi term as pi 1 is equal to rho v delta t by mu, and then second pi term, it is rho raised to a, mu raised to b, k raised to c, v raised to d, and then we are having the delta. By using these conditions we can write the pi 2 as rho v delta by mu, and then the third pi term, that is pi 3, which is equal to rho raised to alpha, mu raised to beta, k raised to gamma, v raised to eta into cp, and which will give you the pi 3 term as mu cp by k, and this is nothing but the Prandtl number. So now we can derive that pi 1 by pi 2 is equal to delta t by delta, and pi 3 is equal to Prandtl number, that is mu cp by k, which is nothing but the Prandtl number as we already described in the last lecture. So this phenomenon of delta t, that is phenomenon of delta t, thermal boundary layer thickness, can be expressed dimensionally as dimensionless form as delta t by delta is equal to function of Prandtl number. So this is the dimensionless form of this particular thermal boundary layer thickness. Okay, so the actual boundary or the actual functional relationship, that is, let's write the actual functional relationship is delta t by delta is equal to Prandtl number raised to n, and for external laminar flow over a flat plate we are having this n is equal to minus 1 by 3. Sorry, it's not like that, there is a small error. N is equal to 1 by 3, and this functional relationship like this, delta t by delta is equal to Prandtl number raised to minus n. Okay, so for that case we can define this Prandtl number and this delta t like this. So the significance of this particular Prandtl number is this. Okay, and also we can write this Prandtl number as Prandtl number is equal to mu cp by k. We can write this as mu by rho into rho cp by k, and we can rewrite this particular equation as mu by rho is nothing but nu divided by k by rho c is nothing but alpha, and this is the ratio of kinematic viscosity to the thermal diffusivity. This is the ratio of kinematic viscosity to the thermal diffusivity, and this kinematic viscosity which gives you, or from this we can understand the how much effectively the momentum is transferred through this particular flow. So this kinematic viscosity is also called as the momentum diffusivity. Momentum diffusivity. And this thermal diffusivity, by analyzing the thermal diffusivity value, we can determine, or we will know the how effectively the heat is transported through this particular fluid. So this is divided by the thermal diffusivity, and this Prandtl number which gives the ratio of this particular momentum diffusivity by thermal diffusivity. Okay, and along these three dimensional numbers, that is Nusselt number, Reynolds number, and the Prandtl number, we are having some other dimensional numbers, that is standard number. Standard number, and this is the ratio of Nusselt number by Reynolds number and the Prandtl number, and this can also be written as H by rho V into Cp. So this is nothing but the standard number, and it is denoted by the letter St. Okay, and along with this, for free convection, we are having a dimensions number called the Grashof number. Grashof's number, which is given, or which is denoted as Gr, which is nothing but the ratio of Bion force into inertia force by inertia force divided by viscous force, the whole square, and this can be written as Bion force divided by viscous force into Reynolds number. So this is nothing but the Grashof number. So these are the main dimensional numbers that we deal in this particular conversion analysis. And let's deal with this particular forced conversion. Forced conversion is nothing but the flow induced by external means. Okay, so that's nothing but the forced convection, and let's particularly deal with the external forced convection. This is a classification of this forced convection in which the flow is around the body that we are considered. So for the plate, for external flow over plate, we can determine this Nusselt number, which is function of Reynolds number and Prandtl number, is not into, it's function of relation number and Reynolds number and Prandtl number, and we can see that this Nusselt number, which is a function of Reynolds number and the Prandtl number. So this Reynolds number is nothing but a quantity, or the dimensionless form, which is function of the distance, or the say this is the plate and this is the flow that is occurring, and this Reynolds number, which is given as for laminar flow 5s by this Reynolds number is a function of, that is over this particular plate. As the length increases, and then the Reynolds number value will changes for external flow, and since this Reynolds number is function of x, this Nusselt number is also a function of x, and therefore we define a term called the local Nusselt number, which is given by a nu x is equal to hx into x by k. So this x is the distance from the leading edge to the point where we considering the value for the Nusselt number, and for entire plate, we define another term called the overall or average Nusselt number. Average Nusselt number, that is Nu bar or NuL, will be equal to 1 by L integral x is equal to 0 to L x equal to 0 to L Nux into dx. And overall heat transfer coefficient, therefore we can determine the overall this overall heat transfer coefficient or the average heat transfer coefficient as this HL by K into L will be equal to this number into L. And from this equation we can find this HL is equal to NuL into K by L. So using this equation we can determine the value of average or the overall heat transfer coefficient. Okay, so that's about the Nusselt number for external flow. And if you are provided or some plate, if you are provided with some plate which is having a length L and which is having a width W into this particular space like this, this distance is nothing but W. And suppose some fluid is flowing over this like this, some fluid is flowing in this way over this particular plate, then we can determine the heat transfer rate by the equation Q dot is equal to H into A into delta T, and delta T is the temperature difference between this particular plate and the fluid, and this is given by H into W into L into T W minus T infinity if TW greater than T infinity. So this is the equation of heat transfer rate for a particular length of the plate over which the heat transfer is occurring, and we can vary this L value depending upon the length up to which we have to determine the heat transfer rate. So that's about the equation that we can use for the determination of this heat transfer rate. And for this case also we are dealing with some boundary conditions. That is basically there are two types of boundary conditions with which we are determining the heat transfer rate or the Nusselt number value. As I already mentioned, this convection analysis is nothing but the determination of the convective heat transfer coefficient value, and from that we can determine the heat transfer rate. Okay, and for the analysis of this particular convective heat transfer ratio or convective heat transfer coefficient value, we have to find the Nusselt number value, and this Nusselt number value can be determined by using various boundary conditions. That is, the first boundary condition is constant temperature of plate boundary condition. That is nothing but the isothermal plate boundary condition, and we are considering for laminar flow over flat plate. We are only considering the flow over flat plate, and for this laminar flow over flat plate we are having this particular relation as Nusselt number Nux is equal to 0.332 into Re raised to 0.5, Rex raised to 0.5, and Prandtl number is to 0.333. And if we are having turbulent flow over flat plate, and we are having Nux is equal to 0.0296 into Reynolds number into X raised to 0.8 into Prandtl number is to 0.33, and this is about the laminar flow. And from this equation we can determine the overall or the average Nusselt number value as NuL is equal to 0.664, Reynolds number raised to REL raised to 0.5 into Prandtl number raised to 0.33, and from this equation we can determine the NuL value as NuL is equal to 0.037 into Reynolds number raised to 0.8 REL raised to 0.8 into Prandtl number raised to 0.33. So these are the first boundary condition, that is constant temperature boundary condition, and the second boundary condition is constant heat flux boundary condition. Constant heat flux boundary condition, or we can write uniform heat flux. Uniform heat flux boundary condition. For that case, if we are provided with some laminar flow, for laminar flow we can write the NUX value as NUX will be equal to 0.453 into Reynolds number raised to 0.5 into Prandtl number raised to 0.33. And if we are provided with some turbulent flow, then this NUX will be equal to 0.0308 into Reynolds number raised to 0.8 into Prandtl number raised to 0.33. So these are the two boundary conditions and the corresponding equations to determine the NUX value, which can be further used to determine the heat transfer coefficient value, that is H, and which can be further used to determine the convective heat transfer rate, which is given by the equation Q dot is equal to HA delta T. Okay, so that's all about the external force conversion. And then the second type of forced conversion, that is internal forced conversion. And in this case, what happens is that the fluid flow is inside some conduit. Fluid flow is inside some closed conduit. Okay, fluid flow is inside some closed conduit. And for that case, the Reynolds number and Nusselt number, and which are having the equations, Reynolds number is equal to rho v L by mu, and this Nusselt number is nothing but HL by K. In these two cases, we are having this L, and this L is nothing but the characteristic dimension. And if we are characteristic dimension, okay, and if we are having circular pipes, then this LC will be diameter. Therefore, we can write this Reynolds number for circular pipes. We are having rho v d by mu, and Nusselt number which is equal to hd by k. And if we are provided with some non-circular conduits, and we are having this LC is equal to 4A by P, and this AC is the cross-sectional area, and P is the perimeter. Okay, and use this particular equation to determine the Reynolds number and Nusselt number for those cases. Okay, so that's about the Reynolds number and Nusselt number for internal flow. And then while dealing with this internal flow, we should define two terms, or we should use two terms, that is mean velocity and mean temperature. For the analysis of internal flow, we will be using this mean velocity and mean temperature. And this is because, suppose we are having some internal flow like this, and consider this as the conduit or the pipe through which the flow is occurring. And what happens is that, and this is the center line, of this particular pipe, and whenever some fluid is entering into this pipe like this with velocity u infinity and temperature T infinity, what happens is that there will be no slip condition at the wall for the velocity case. First I will discuss the hydrodynamic boundary layer and those mean velocity first of all. And for that case, what happens is that here this there will be a difference in velocity with respect to the wall and the velocity and the fluid. So what happens is that at the boundary or at the wall, there is no slip condition, that is velocity will be 0 at this particular wall, and then from the wall what happens is that the velocity variation will occur, and this variation will be present up to the center line of this particular pipe like this, and we can draw the velocity distribution as, and there will be variation over here, and this particular region there is no variation in the velocity, and this here there will be again variation, and this will be the temperature profile, and see there is some variation in this temperature profile over here, and let's in the course of the or in the along the length of this particular pipe, this boundary layer will generate from the top and bottom surfaces, and this temperature or the velocity variation will also change like this, and the region with uniform velocity will be reduced, and the region with temperature variation velocity variation increases, and the velocity distribution will be like this, and after reaching certain point then the velocity distribution will be like this, that is a constant variation from top and bottom to the middle portion of the or the center line of this particular pipe, and this is the parabolic curve. Okay, and up to this distance from the entrance point it is called the hydrodynamic entry length, hydrodynamic entrance length. Okay, and beyond this particular entrance length or this particular length of this particular pipe, what happens is that the velocity will be uniform. Velocity will not be uniform, but it is having the uniform parabolic profile. Okay, uniform profile. But in the case of this particular pipe flow, the variation of this fluid or the velocity profile is parabolic in nature, so we have to define some particular velocity which is uniform, and there is no variation in the profile, which will provide the same flow rate at the exit. So let's suppose I will draw it in some other color. So let's suppose for this particular we are creating some other velocity, that is mean velocity, which will give you the exact same flow rate at the exit of that of the original velocity that is existing in this particular flow. Okay, so this is mean velocity, and this is v, that is the exact velocity, and this is the mean velocity distribution, mean velocity distribution, and this is for original velocity distribution, so we have to define the term, we have to define this particular value Vm, and this Vm is given by the equation 1 by a integral v into dA, and this Vm is the mean velocity that we define, which will produce the same flow rate the exit as that of original velocity. Okay, so that particular velocity is called the mean velocity, and this is all about the hydrodynamic boundary layer and this flow in pipe, or the velocity distribution and the mean velocity case in the internal flow. And let's suppose the same internal flow over the same pipe like this, and we are having some fluid that is entering into this pipe in this direction with velocity u infinity and temperature T infinity. We are having the temperature of the valve Tw. Let's suppose we are having Tw. Let's suppose we are having Tw is greater than T infinity. For that case, what happens is that, as similar to the case with thermal hydrodynamic boundary layer, at the walls there will be thermal boundary layers which will generate because of the temperature difference between this particular wall and the fluid, and this will meet these two boundary layers that will meet at the center along the length, or as the length progresses. Okay, as the flow progresses along the length. So the boundary layer will be like at this entrance there will be a less, at the entry region there will be a less temperature difference or the thermal temperature variation like this, and here the temperature will be constant, that is T infinity, and here also the T value will changes. Okay, so this will be the temperature variation, temperature profile at the entrance or the just after the entrance. And then if we move along the length and let's suppose some region, and here suppose here we can see that there is a more elaborate region of this temperature variation, and there is a less region with a constant temperature. This is the temperature of the fluid, and this is the temperature variation in this region. And what happens is that beyond certain length, or beyond the length at which the boundary layers meet, we are having some uniform temperature profile like this. Okay, it's not uniform, but the temperature variation will be like this after this particular length, and up to this length from the entrance of the pipe, which this distance is called the thermal entrance length. Okay, so that's about the entrance length in this particular thermal flow. So in this case we will be defining another term called the mean temperature. And this mean temperature is defined by using a similar condition as of the previous case, that the hydrodynamic entrance length, or the flow through the hydrodynamic analysis, flow through the internal pipe. And here we are considering the equivalent energy flow rate, and which means I will explain that the temperature profile, or the temperature which will give you the same energy flow at the exit. Okay, so this particular temperature is the mean temperature profile, and this is the actual temperature profile. And this particular Tm, that is mean temperature, which will give you the same flow rate at the exit, that will be facilitated, or that will be provided by the actual flow rate. So the mean temperature is defined as, or the mean temperature is given by the equation Tm is equal to 1 by Vm into A into integral T into V into dA. So this is the equation that we use to determine the mean temperature. Okay, and this is given by the equation considering the same energy flow rate, that is m dot into Cptm will be equal to integral Cpt into dm, and which will give you rho b m into a into cptm will be equal to integral cpt into rho v into dA. And for constant density, if density comma cp is constant, then we can write this particular equation as vm into a into tm is equal to integral t into vdA. And from this equation we can determine this particular equation, that is tm is equal to 1 by vm into integral t into vdA. So that is the equation for the mean temperature. And we are having the bulk another term called the bulk mean temperature. Bulk mean temperature, and this bulk mean temperature is given by the equation T bar is equal to Tmi, that is mean temperature of the inlet, mean temperature of outlet divided by 2, that is the average of the mean temperature at inlet and outlet.